next speaker in this afternoon session, who is Dawid Kielak, and he will tell us about virtual fibering and Poincaré duality.
Okay, thank you very much. Yeah, thank you for having me. In fact, I spoke only once in the INI before. It was exactly at the main semester that this is kind of follow-up to. So it's nice to be back here. Okay, I should also apologize for giving a slide talk when we have such a beautiful blackboard, but that's life. Okay, virtual fibering and Poincaré duality. So let me start with fibering. So what is the entire game about? So I'm going to tell you about why we want to, given a manifold, so somehow the background of the talk is all about manifolds. Okay, I mean, it's really about groups, of course, but we pretend it's about manifolds. And we're going to discuss why you would like to show that the manifold fibers over a circle. And once I convince you that we want to do it, then the second question is, how do you arrange for the manifold to fiber over the circle? How do you check that it does? Okay, that's the main point. Okay, so straight away, let's get the definition out of the way. I'm going to stay in the smooth category for convenience. So I have a smooth manifold M. The manifold is going to be connected and compact and orientable and usually also aspherical. And I'm going to look at a smooth map from the manifold to S1, the circle, and that's going to be called a fibration. If and only if the following happens, I can cover my circle by a bunch of open sets U, such that if I look at the pre-image of this open set U, or each of these open sets U, my space decomposes as a product, it's diffeomorphic to a product, in such a way that the map F from the manifold to the circle is just the projection onto the U factor, okay? That's the formal definition. So what's happening? You take a point in the circle, you look at the pre-image. The pre-image is kind of a slice of your manifold. As you move around the circle, every point gives you a different slice, but they all look the same. So as you move around the circle, the slices deform in a continuous manner. That's what we want, okay? We want to be able to slice our space in such a way that the dual picture is in S1. If we manage to find such a slicing, then, well, first of all, because we are in the smooth category, you can see that the fiber is going to be, so there's something wrong with the slide, sorry. Okay, right. So since S1 is connected, you can see that the topological or the diffeomorphic type of this Z is actually independent of which U you're looking at, because when you pass from one U to the next, the Z is always the same. So the Z is called the fiber, and this fiber is always a manifold in the smooth setting, and it's a manifold of dimension 1 less. Okay? So the game that we're trying to play here is that if we manage to get this fibering, okay, I bought Cornelia already. So if we manage to get this fibering going, then we have identified an interesting co-dimension 1 submanifold. And moreover, our big manifold looks like this smaller manifold kind of wrapping around over the circle and then getting glued to itself in some way. Okay? So, and one thing to mention, since I will mostly care about aspherical manifolds, if M is aspherical, the fiber is automatically also aspherical. That's easy to see. Okay, so now let's just have kind of a thought experiment. What would happen if we change the S1 into an interval? So if I was looking at a fibering over the interval, I would just these local trivializations, these structures of a product, would become a global structure of a product. My space would just become the fiber times the interval. Okay, so that's not super interesting, but because the interval actually gives you the circle when you glue the endpoints, what happens here is that you see exactly the picture I was trying to describe a second ago. So you have the fiber, you times the interval, and now you glue the top to the bottom in some complicated way. And that's the structure of your manifold. Okay? So once you manage to show that your manifold is fibered, you can, over the circle, you can think of it as a codimension 1 manifold and this gluing map. The gluing map is called the monodromy. And here's kind of a simple example of what can happen. Imagine that the manifold you start with is just an interval. When you have a fibering of some manifold over the circle where the fiber is an interval, only two things can happen. You take the interval times another interval, you have a strip, and now we are gluing one end of the strip to the other. It's either an annulus or a Möbius band. Okay, because there are essentially only two interesting diffeomorphisms of the interval up to homotopy, the identity and the flip. Okay? So this is a very simple example which shows you that something interesting can happen. If you take the monodromy not to be the identity, you do not get the product, you get something else. Yeah, something which is richer than the product. Does it make sense? Okay, so here is kind of the slogan that's meant to convince you that we should really care about this. If you give me a nice manifold and I want to understand it, and I do manage to show that it fibers over the circle, then I'm reducing the study of this static object in dimension n to an object of dimension n minus 1, which is changing in a dynamical way. We have the monodromy, and I can think of the monodromy as a dynamical system. I'm going to apply the monodromy over and over and over again to my manifold, and the dynamics of this is going to show up. Okay? So I'm trading a static n-dimensional object into a dynamical n-1 dimensional setup. Okay? So this is a double win. First of all, I win because I drop the dimension. Secondly, I win because I'm bringing in the tools of dynamics into the game. Yeah? I'm losing the staticity of my manifold. I'm gaining the dynamics. Okay? So this is what we want to do. If we manage to do it, you can learn a lot. In particular, you can learn a lot in dimension 3. So if we start with a 3 manifold, and we manage to show that it fibers, then the fiber is a 2-dimensional manifold, so it's a surface, and the monodromy is a diffeomorphism of the surface, and we only care about everything up to homotopy, so it's a mapping class. Okay? So we have very, very detailed understanding of surfaces, and we have very good understanding of mapping classes. So in dimension 3, the moment you show that your manifold fibers, it's over. Okay? You essentially know pretty much everything you want to know about. So here's another little diagram. When the point moves over the circle, these surfaces, the fibers, they kind of move through your space. Yeah, so we understand both ingredients extremely well. We have the Danius and Thurston classification of mapping classes, and we understand, at least topologically, all surfaces very, very well. So in dimension 3, it's certainly kind of game over at this point. So we really want to do this. Okay, we really want to be able to fiber a manifold.
But can you tell in dimension 3 how many actually?
If there's at least one and the Abelianization is of dimension at least 2, there's infinitely many. Yeah, but it's an interesting question how to, but I'm not going to talk. In fact, I talked about exactly this last time I was here, about the structure of different ways of fibering. So, yeah. So you should remember, Gulnara, you were there.
Actually, you answered a different question. My question was among 3 manifolds.
Oh, how many fiber?
How many which fiber over the
So fiber on the nose, not so many, but you will see in a couple of slides that almost all of them virtually fiber. So when you allow yourself to pass the finite index cover, almost all of them. It's a very, very common feature. Okay. By the way, I'm very happy to answer questions. Yeah, not just from Gulnara. If anybody else is brave enough. Okay. So now let me stop pretending that we are doing topology, and we are going to go straight into group theory now. So if I have a fibring, a fibration, I start with a map from the manifold onto the circle, and this map is going to be non-trivial homotopically. So it's going to give me an epimorphism from pi1 of m to z. Bear in mind, I'm not saying that this z is exactly the pi1 of this s1, because we might not be onto. Okay, so there's like a slight cheat in what I'm saying here. But anyways, you should think about applying the pi1 functor. The manifold becomes a group, s1 becomes z. The fibration becomes a map, a group homomorphism from the fundamental group of m to z. Yeah, I'm happy about that. Okay, so now here's the main player in this game, a beautiful theorem of Stallings from 1962. And I'm giving a slight reformulation of it, which incorporates the resolution of the Poincaré conjecture. If you take a compact 3-manifold M, if you take an epimorphism, phi, from the fundamental group of M to Z, then this exact map is going to be induced from a fibering. So it's going to come from the manifold fibering over the circle and pi1 applied to this picture. Okay? If and only if the kernel of phi is finitely generated. Okay? So if I had a 3-manifold which fibered, the fiber would be a surface. Yeah? The surface is a compact surface. The fundamental group of a compact surface is definitely finitely generated, and the fundamental group of the fiber is exactly the kernel. So if I had topological fibration, I would definitely get this, and much more. Okay? I would know that the kernel is actually either 3 or a surface group. And Stallings says that it's enough to require this very, very rudimentary algebraic knowledge or understanding of the kernel of phi, the fact that it's finitely generated, to be able to rebuild the whole topological picture. Out of this very little, you get the fiber being a surface and the full vibration picture. Yeah, so this is a remarkable result. Okay, so there is some kind of a connection, at least in three manifolds, a strong connection between fibering in the topological sense and properties of the kernel of a map to Z. So this immediately begs the following definition. I'm going to say that a group is algebraically fibered if and only if it admits an epimorphism from G to Z with a finitely generated kernel. Okay? Moreover, given such a map phi, I will call it a fibration if and only if its kernel is finitely generated, and so on. Yeah, so it's the same picture. Somehow I have the topological picture on one side, the algebraic on the other side. Being a fibration on one side is the same as having finitely generated kernel on the other side. Yeah? So this is kind of the, in three manifolds you have this perfect analogy between the algebraic and the topological setup. Okay, right, so answering Gulnara's question, some manifolds, in particular some three manifolds, do fiber, but this is not so common. But what is extremely common is that if you allow yourself to pass to a finite index subgroup or to a finite sheeted cover, you might improve your situation, you might become fibered. Yeah? So this is something that we want to understand, because this really happens. In fact, it happens quite a lot. So now we are going to connect to the negative curvature topic of this conference. It was a conjecture of Thurston, and it's now a theorem of Agol and Weiss, the virtual fibring conjecture, that if you take any finite volume hyperbolic three manifold, then up to passing to a finite cover, it is actually going to fiber. Okay? So they're all virtually fibered, finite index subgroups or finite index finitely sheeted coverings, fiber over the circle. So it's very common. And in fact, lots of other three manifolds have this property. We understand exactly which ones are virtually fibered, and it's almost all. Okay. So so now let me introduce the following audacious conjecture. So okay, for hyperbolic three manifolds, this is the case. Maybe it's the case for all finite volume hyperbolic manifolds in odd dimensions. Okay? Maybe. Go ahead.
And why can't you have even dimensions?
Since
Since you're not looking for fibers?
I will tell you. So the reason why I'm not allowing even dimensions is Euler characteristic.
But that would just prevent you from being a bundle over a circle.
Yeah, but all
here
over the
you're only
circle.
having...
No, sorry, just all over the circle. When I say fibered, I mean over the circle. Sorry, I should have made it clear.
Yeah, no, but here you're... Yeah. But here what all you're asking when you talk about fibering is a map to the circle such that the kernel...
No. This is honest to God fibering.
Oh, genuinely. Oh, yeah, there's Euler characteristic.
Yeah, exactly. I was getting that. Yeah, right. So some of you already know, right? So why? So this is genuine fibering, not in the algebraic sense. This is the topological fibering. Okay, this is what this conjecture is about. The conjecture is about a manifold, a map to the circle, which is a fibration in the topological sense, as I introduced in the first slide. Okay, that's what the conjecture is about. Why odd dimensions? So if you have a hyperbolic manifold in even dimension, it has always non-vanishing Euler characteristic. And Euler characteristic of a space which fibers over the circle is always 0. Okay, exactly for the same reason why taking the product with the circle always makes your Euler characteristic 0. It's a very easy exercise. Yeah? So all even dimensional hyperbolic manifolds have exactly 0 chance of satisfying this conjecture. Yeah? However, for odd dimensional hyperbolic manifolds, who knows, it might be true. Okay, so just one thing I wanted to say. So there are two styles of conjectures, as they say. There is the Russian style, which is the weakest statement to which you have no proof. And there's the French style, which is the strongest statement to which you have no counterexample. And that is very much a French style conjecture. Okay? So the conjecture is kind of crazy, but you know, why not? So evidence. We have strong evidence in dimension 3, because in dimension 3 the conjecture is actually true. And in dimension 5, we have a single example due to Italiano, Martelli, and Fiorini from 2023. There is a finite volume fibered hyperbolic manifold in dimension 5. We don't have any closed example, but we have a finite volume example. However, there's also some bad news coming from the paper of Avramidi, Open, and Shribi, 2024. In dimension 7, if you relax your assumptions and you no longer look at a hyperbolic manifold, but only at a manifold with a hyperbolic fundamental group, Gromov hyperbolic fundamental group, then there actually are examples in dimension 7 that do not virtually fiber.
Do you know if Stallings' theorem does not hold in higher dimensions? Like, are there maps to Z with finitely generated kernel that are curvature?
So for manifolds in even dimension, you can definitely construct such maps. Yeah.
But what about odd dimension?
Yeah, yeah. So I mean, if you in the Gromov hyperbolic setting, yes.
They're not HN, right?
There might be such context. Also, Kyle's theorem tells you the obstruction is in K theory.
Yeah, but the K theory of the hyperbolic.
But the kernel could be presented, but not.
Well, in principle, it's good because we have explicit examples. I mean,
Well, this Claudia and PRT pi.
Yeah, but are they manifolds?
Yeah, they're complex supporting maps.
Okay, so yeah, the answer is yes. Okay, so Claudio.
Complex hyperbolic?
No, I think so.
So I'm pointing Claudio's work. Is Claudio here?
I think those are complex hyperbolic.
Complex hyperbolic.
Yeah,
I see.
complex hyperbolic.
Yeah, okay, but that doesn't count. So I don't know. I mean, they're not hyperbolic. So the answer is I don't know. I don't have an explicit example.
David?
Yeah.
These the examples in the last theorem, are they known not to be hyperbolic manifolds, or is it not?
They are. I mean, the construction gives you a manifold which is not hyperbolic, but I mean, whether they could also be fundamental groups of honest to God hyperbolic manifold, I'm not sure. I mean, whether Borel conjecture is true for these guys or not, I don't know. Yeah, I don't know. Okay, any more? Good. Okay, so this is there is the theorem, a crazy conjecture, some very weak evidence, and some maybe bad news. But at least for the bad news, we understand exactly where the bad news comes from, and I think that this should not be a problem for honest to God hyperbolic manifolds. Okay, so at least I sleep well at night with this. Okay, but now I want to explain why I think this conjecture has maybe a chance of being true. Okay, so I'm going to try to sell this conjecture to you, and to do that, I have to actually go into Agol's proof of virtual fibering for hyperbolic three manifolds in some detail to kind of introduce some important properties. Okay, that's going to help us. Yeah. Okay, so here's how the proof of Agol's works. So I'm going to present the entire proof in very broad outline, and I will do it in the logical sequence and not chronological sequence. So it will all kind of go backwards in time. So logically, we start with the paper of Kahn and Markovich, where they proved that a hyperbolic three-manifold, closed hyperbolic three-manifold is going to contain many quasi-Fuchsian surfaces. Okay, if you don't know what quasi-Fuchsian means, don't worry about it. If you are given some mysterious manifold, okay, Martin is not here, but you take a manifold from the gutter, you all know, and then you want to check that it's fibered. So if it is fibered, you're going to have the fiber. The fiber is a surface. Okay? So if a manifold, a three-manifold, has any chance of fibering, there better be surface subgroups inside. Now that was an open problem, and Kahn and Markovich found surfaces inside. They did the surfaces they found are quasi-Fuchsian, so they're actually not the fibers, but it doesn't matter. Okay, there are better behaved surfaces than that. And out of the existence of these quasi-Fuchsian surfaces, so you should imagine you have your three manifold, and the surfaces are kind of going everywhere, and they cut your space. And what you do is you put a vertex in every component after the cutting, and you connect two vertices with an edge if they are on two sides of a single surface. If there are two surfaces crossing like this, you get 4 points, you put in 4 edges, you fill in the square, and so on, and you build a Q complex like that. Okay? So this is the construction of Bergeron and Weiss, and they prove that because of the existence of these quasi-Fuchsian surfaces, the fundamental group of the manifold is going to act properly and co-compactly on a cut-zero Q complex. Obtained as I kind of tried to indicate. Okay, then comes the final bit of the proof, Agol's theorem, and Agol proves that this Q complex is actually virtually special, out of which, going back in time, Haglund and Weiss allow us to show that G up to finite index, and the virtually comes from this virtually here, up to finite index, G is actually a subgroup of a right-angled arting group, and then with this audience I don't have to define it, which is great. So G up to finite index, sits inside the rag, and then every subgroup of a rag is reverse, and I will define it on the next slide. So our group is virtually reverse, and here comes the the final bit of the logic of the proof. Agol proved that if you take an irreducible three-manifold with fundamental group being Riefers, then it virtually fibers if and only if the Euler characteristic allows it to. Okay? In particular, if you take a closed manifold, three-manifold, the Euler characteristic is always 0. Okay, so that's the proof. So there is this whole yoga of the first 4 bullet points. And the whole purpose of this yoga is to prove that the fundamental group of the manifold has this useful property Riefers. And then, using the Riefers property, you actually construct topologically a fibring provided the Euler characteristic doesn't obstruct it. Yeah, that's how the proof goes. So 2 steps. First, you torture the group long enough until it admits to being Riefers, and then you use this property to build the topology. Okay? That's how it goes. Okay, so now I'm going to tell you what Riefers is. First, before defining Riefers, I have to remind you what a poly Z group is. So imagine that you start with a trivial group, and now you allow yourself extensions by Z. Okay? And you do it finitely many times. All the groups you will construct are called poly Z groups. Yeah, so poly Z means you have a map to Z, and the kernel is poly Z of lower class. And when you get to class 0, you're trivial. Yeah, so it's a very, very easy class of groups. And here's the definition. So at least for countable groups, you are Riefers if and only if you are residually poly Z and virtually abelian at the same time. Okay? So you have a residual chain of normal subgroups. When you take the quotients are at the same time poly Z and virtually abelian. Okay? Very easy. Okay, very easy groups. Poly Z, virtually abelian, I mean, it's hard to think of easier classes of groups to deal with. Yeah? So this means that your group has lots and lots of very easy to understand quotients. Okay? That's what Riefers is. Pretty happy about that? Okay, so that's what you have to work quite hard to show that the group has this property, but that's what it is. Okay, and now it's very easy to see it's a residual property, so it passes to subgroups, and it is also not super hard to show that it holds for right-angled outing groups, so it will hold for all special groups, compact special groups. Okay, so back to Agol. So this is the main step the kind of final step in Agol's proof, the one which allows you to turn algebraic knowledge into topology. And then one can ask, how far can you go if you forget about the topology entirely and you just want to do things algebraically? Okay? You just forget about the existence of topology and you just do group theory. So something I proved some years ago is that for Agol's theorem, remember that being virtually fibered for 3 manifolds is the same as having a finite index subgroup which maps onto Z with finitely generated kernel. That was Stallings' theorem. Yeah? So it turns out that if you think about it that way, then it's not actually a theorem about 3 manifolds. There's a statement which holds for all infinite Riefers groups. So if you take any infinite Riefers group, it's going to be virtually algebraically fibered. So again, it admits a finite index subgroup mapping onto Z with finitely generated kernel, if and only if the first L2 Betty number vanishes. Okay, so this is the usual first L2 Betty number. I'm putting the Q in here because later on I will actually already here we will talk about slightly different versions of it. Okay, I will talk about L2 homology after that, so don't worry if you haven't seen it. But the point is that there's a single piece of homology. This is just one dimension of one vector space that captures the information about whether your group does admit or does not admit virtual epimorphisms to Z with finitely generated kernels. Yeah? And also I should say I'm not lying here, I'm not cheating here. So if you've seen Luke approximation, you might think, okay, this is all just trickery because in fact to understand this number I have to know something about all finite index subgroups to start with. Not true, okay? I can compute the first L2 Betty number without knowing anything about finite index subgroups at all, and it will inform me about the existence of some particular finite index subgroups with good properties. Yeah? So it's a global invariant, you compute it for the group itself, and it tells you about what happens when you pass to finite index. Yeah? Okay, and then Sam Fisher proved a more general version of this. So I focused here on being algebraically fibered, so finite generation of the kernel, and it turned out that the right object to look at is the first L2 Betty number. But Sam proved that if you take a Riefers group, it will admit a virtual epimorphism to Z with kernel with better properties, and we'll discuss it in a second, if and only if more of these homology groups vanish, okay? So if you want this kernel to have this good property up to index n, then you want vanishing of your L2 homology up to dimension n. And what's happening here with this field, so L2 homology has kind of a variant. I mean, L2 homology is naturally a characteristic 0 variant, but there are also positive characteristic versions due to Andre, and this is what they are. If you take k of different characteristic than 0, then you have a different way of computing them, and it turns out that they control the behavior of your kernel from the algebraic perspective over this particular field that you have.
How does the Z question relate to doing a characteristic P for all P?
You mean this?
Yeah, this FPN.
So if you can get an FPN over all fields at the same time?
Yeah.
You can do that. I will get to that at the very end. Okay, so let me explain what this nice property is. Okay, finiteness property. It's a quick slide. I'm sure you've all seen it a million times. But what is good? So if you have a group which is finitely generated, then you can always construct a classifying space which has finite one skeleton. Okay, you take a single vertex, a single edge for a generator, and then you go on. So being able to construct classifying spaces with finite skeleta is a good thing. It's kind of better than being finitely generated. If you have a classifying space with finite 2 skeleton, then you're finitely presented, and so on. Yeah? So these are kind of better and better properties relating to how nice and how well behaved your group is. So if you have a group with such a classifying space, then what you can do is you can take the cellular chain complex of the universal cover. Okay? So X is a classifying space, so it's aspherical by definition. The universal covering is homotopy equivalent to a point. That's again the definition. So when I'm taking the cellular chain complex of in a spherical space, I'm computing the homology of a point. Yeah? The homology of a point lives in dimension 0. It's a single copy of Z. So that means that this chain complex, the cellular chain complex of X tilde, is exact, except at the end I'm getting a copy of Z. So I'm going to put this copy of Z here, and now I get an exact sequence. Yeah? I could put a 0 at the end. So such a thing is called a resolution. This is a resolution of Z by projective ZG modules. These guys are actually naturally free Z modules, but it doesn't really matter. And the important thing is that because I took X to have finite n skeleton, I'm going to have these guys finitely generated up to degree n. Because each of them is a direct sum of a number of copies of the group ring, and the number of copies is exactly the number of cells of that dimension in X. That's all it is. Yeah, it's an easy exercise. Okay, so if I have a good space, a good classifying space, I'm getting a good resolution. But now, if you came from a planet where people didn't discover topology, they would know about resolutions, so they would introduce the following definition, that instead of thinking about spaces from which it comes from, you would just say that the group is nice, so you would call it of type FPN, if it admits such a resolution. Okay, so there is a resolution of the trivial ZG module Z by 3 ZG modules, which are finitely generated up to degree n. Yeah, this is the algebraic version of a finite classifying space. Okay, but now in algebra you have the freedom of changing your coefficients. So if I replace every Z, so this Z, that Z, and that Z, if I replace them all by a field K, it gives me type FPNK. Okay? So FPNK means that homologically speaking, and if you only know about coefficients in your favorite field, your kernel, let's go back to the previous slide, it's all about this thing here. Your kernel being of type FPNK, it means that it behaves as if it came from a space with finite n skeleton. We are trying to make sure that it comes from a fiber. The fiber is going to be a compact manifold. Okay? It's going to be of type F. It has finite skeleton in every dimension. So this is definitely something that we want to be able to say, right? We want to be able to get as good properties as we can, and as high as we can, and as great a variety of fields as we can. Okay? Did it convince anybody? Maybe not. Okay. So anyway, so Fisher tells us that if we care about this problem, about these homological finiteness properties, we have to start studying these more complicated versions of L2 homology. That's the upshot of that. Right. Okay. Plenty of time. So I tried to sell to you why we want to fiber manifolds, and I tried to sell to you why we care about refers, and now I will try to sell to you the notion of L2 homology. So this is a tangent, okay? Has nothing to do with what I said so far. So what is L2 homology and why is it important? Why is it useful? So what we are really trying to do is we are trying to compute the Euler characteristic, okay? As we've seen in Agol's result, for example, if a three-manifold has refers fundamental group, it's going to fiber, eventually fiber refer only if it has vanishing Euler characteristic. So we want to compute the Euler characteristic, but we want something a bit better. So Euler characteristic is a nice invariant, but it's a single number for the whole object. Okay? And what we want is we want a sequence of invariants that live in different dimensions, different degrees, and they behave as well as Euler characteristic. That's what we want. Okay, so how can we compute the Euler characteristic? So the easiest way, maybe the definition of Euler characteristic, is that you take a space. In this case, we are going to take a classifying space for a group, right? And we are going to take the alternating sum of the numbers of cells in each dimension. Yeah, this is the V minus E plus F definition of Euler characteristic. Now, what is good about these numbers of cells? If I have a space X and I take a finite covering of the space, the numbers of cells in each dimension go up multiplicatively with the index of the covering. If I have 100 sheeted covering, every cell downstairs becomes 100 cells upstairs. Yeah? So the number, being the number of cells in a given dimension, is good because the alternating sum gives you Euler characteristic, and it behaves very well with respect to finite coverings, which is something we want. However, it is not a homotopy invariant. Yeah? You can take a different space with the same homotopy type and has different numbers of cells. So that's not good. Okay. Alternating sum of Betti numbers, this also gives us the Euler characteristic. This is a homotopy invariant. What happens when you pass to finite covers? Well, God knows what happens. Okay? Homology is notoriously difficult to compute when you start passing to finite index coverings. Weird things can happen. There's no good behavior. Okay, and here we have the L2 Betti numbers. So L2 Betti numbers, first of all, the alternating sum gives you the Euler characteristic, so that's 1. They're homotopy invariant, so that's 2. And when you pass the finite covering, they scale up with the index of the covering, so that's 3. Okay? So L2 homology does what Euler characteristic does, but in every degree separately. That's why we care. Okay? That's the reason why it's a good notion of homology. Okay, but I didn't tell you how it's defined, but I will do it now. Okay, so for a refers group, this is the definition. Don't worry about this. So the definition of the L2 Betti number of some particular characteristic, I mean, it's a Betti number, so it should be the dimension of a homology group. The homology you take is the homology of your group G with some particular choice of coefficients. And this coefficient choice is a skew field containing the group ring. So because it's a field, it's a skew field, this guy is a module over this, right? And modules over fields are free. They are vector spaces, and they have well-defined dimensions. So the L2 Betti number is just the dimension as a DKG vector space of this particular homology group. Okay? So this definition only tells you something if you know what D is. So when you work over the kind of classical coefficients, the rationals, this field is the division closure of the group ring in the algebra of operators affiliated with the group von Neumann algebra of G. Okay? What's the purpose of this sentence? Just to tell you that there's some functional analysis happening in the background. Okay? So now if you want to change fields, then you have to pass to a different construction of the fields. And this is due to Andre. I'm sure he'll be very happy to answer all of your questions about this construction during the break. Okay, so now we've seen the honest to God definition, and let's move on. So back to Agol's theorem. So Agol says an irreducible three-manifold with refers fundamental group virtually fibers if and only if we had the vanishing of Euler characteristic on the previous slides. But due to the work of Lott and Luck in '95, they computed L2 homology of three manifolds, and it turns out that instead of requiring the Euler characteristic to be 0, you can equally well require all of the L2 Betti numbers of the manifold to vanish. Okay? So this is just a reformulation of Agol's result, that for refers fundamental, three manifolds with refers fundamental groups, it is exactly the vanishing of all of L2 homology which controls virtual fibering. Yeah? That's exactly what it is. Moreover, if you take any topological space X, it's going to virtually fiber over the circle with a compact fiber. If it does, then all of the L2 Betty numbers of the space X, or of the fundamental group of X, will vanish in all characteristics. Okay, so this is an extremely general fact. It has nothing to do with Riefers. Anything that fibers over the circle will have vanishing Euler characteristic. It will also, in fact, have vanishing of all of these L2 Betty numbers in all characteristics. Yeah? So this is just, it's a must. If your manifold is to fiber over the circle, all of these L2 homologies, they have to vanish. Yeah? There's no escaping this. So the interesting question here is, to what extent is this the only constraint? And what Agol's proof shows is that for 3 manifolds, it is the only constraint. Yeah? There's nothing else. Just that. Okay, so now I'm coming to the second part of the title, Poincaré duality. So what is a Poincaré duality group? So, I mean, let's start backwards. What you should definitely bear in mind is fundamental groups of closed aspherical manifolds. So if you take a fundamental group of a closed aspherical manifold, because we are looking at an aspherical manifold, the homology of the group and the homology of the manifold are the same thing. Yeah, by definition, if you want. So if I have a manifold, I have Poincaré duality. So, you know, in your head, you're replacing this G with the manifold that it came from. And Poincaré duality is going to tell you that the ith cohomology of the manifold is the same as the n minus ith homology of the manifold. Okay? So the definition of a Poincaré duality group is a group which essentially does the same thing. First of all, we have to require that the group is of type FPN. So it has to, again, from the homological perspective, it thinks it is a fundamental group of a compact space. Okay? And secondly, if I take any choice of coefficients, any G module, and I look at the cohomology in dimension I and the homology in dimension n-1, they are isomorphic. Okay? You can also say that they are naturally isomorphic, and there are other ways of saying the same thing. Yeah? So just the duality between homology and cohomology, as we are all used to in the case of manifolds. Okay, so this is I should also say, so there are 2 definitions of Poincaré duality. There's one due to Wall, where you also require the group to be finitely presented. And this one is due to Beery. Actually, it appears in Beery's thesis, where you don't require finite presentability, and I definitely want to stick to this one. Okay? It is a much more natural definition, the reason being that everything is purely homological. Okay? Finite presentability has no meaning homologically. Yeah? So one stays here entirely in the homological world. Okay, go ahead.
You want to assume that the isomorphism is induced by a cap product with the fundamental class?
It is also true, and it follows actually from it. So you don't need to assume it, but it's another way of saying the same thing. It's very interesting that you can get many much stronger properties just from that. Actually. Yeah. You don't need it.
Are you assuming the resolution is over the whole numbers, or it doesn't really matter?
The resolution is over
the whole numbers?
Z. Yeah, this is over Z. Yes. Okay. So maybe I didn't say it explicitly. So this is what a Poincaré duality group is. But you can also say this is over Z, and this is over Z, and this is a ZG module. But it's exactly the same thing. Okay. So when I say FP, I mean over Z. When I say a G module, I mean a ZG module. Okay. But now it's going to become important because we're going to decorate it. So you can also think about Poincaré duality groups over fields. The only difference is that you require less. Okay. It's not that the group thinks it's coming from a compact space. Only when you look at the homology with k coefficients, it thinks that it comes from a compact space. And again, you have all the isomorphisms you want, but not for all G modules, but only for kg modules. Okay? This might seem like it's not a big deal, and maybe it really isn't a big deal, but somehow we need to assume it. Okay? Does it make sense? So this is the setup I want to work in. I want to look at these Poincaré duality groups over some particular field. Now, what do we know about Poincaré duality groups? So up to dimension 2, the only Poincaré duality groups are fundamental groups of spherical manifolds. In dimension 3, it's open. In dimension 4 and above, it's false. However, it is open when you also require finite presentability. Okay? So it's entirely possible that if you add in finite presentability, we are talking exactly about fundamental groups of spherical manifolds. Yeah? It's not clear. Okay. And here is the new result that I wanted to advertise. It's on the archive. It's with Sam Fisher and with Giovanni Italiano. So what did we prove? So remember, the whole talk is about fibring manifolds, but now we are moving completely into the homological world, and we replaced manifolds by Poincaré duality groups. So if I take a Poincaré duality group, which is also reverse, and is Poincaré duality over some particular field of your choosing, it's an n-dimensional Poincaré duality group over K, then we have the following equivalence. So there exists a virtual epimorphism onto Z, okay, so the group admits a finite index subgroup, that finite index subgroup maps onto Z, and the kernel of this map is actually itself a Poincaré duality group of dimension n-1 over the same field. And that is equivalent to the vanishing of all of L2 homology over K for our group G. Okay? So this is kind of what we were, I mean, if I could say the exact same thing about manifolds, I would be extremely happy. Yeah? But for now, this is only about Poincaré duality groups over fields. But this is really, it's the thing that we want. You take a Poincaré duality group, you take a finite covering, you map it to Z, and you get a kernel, which is itself a Poincaré duality group. Okay? So it is exactly what you want. It's exactly the right sort of statement you want, or you would want in the topological setting. And it turns out that the only abstraction is the vanishing of this L2 homology. And of course, the reverse here plays crucial role. Okay, this is only for reverse.
So
yeah.
The Poincaré duality groups that aren't finitely presented, so are their L2 value numbers also 0? Do they fall into this?
Single conjecture,
yeah.
It's open. Yeah. So the single conjecture would tell you that if you take an odd-dimensional Poincaré duality group, then it should have no L2 homology.
Protest a little bit.
Yes, go ahead.
So you have a lot of conditions, and each of these conditions are really, they are all very restrictive. I mean, it's already very difficult to find epimorphism onto Z, and then you would like to have a kernel in addition to be finitely presented in addition, etc. And then G should be this reference, which is very restricted. I mean, do you have examples?
Yeah, like hyperbolic free manifolds, for example, all fit into this.
Or
yeah. And many, many more. All arithmetic hyperbolic manifolds in all dimensions will be reverse. And there will be examples of this. In dimension, all arithmetic ones in dimension above 9 are simplest type, right?
Really?
I think so, yeah. It's in the paper of, Alan is saying no, so I should be careful. I thought it's in the paper of Danny with Bergeron.
No, the simplest type ones are virtually.
Yeah, but so other examples of arithmetic. Are you okay? Okay. Well, I'm not going to argue with Alan, so apparently it's yeah. Simplest type. Anyways, there's lots of examples. Yeah, lots and lots of examples. So I mean, this part is restrictive, not super restrictive in my opinion, but it is. This is not restrictive. That's what you get, right? This is what you want to compute, and this is what you want to get. So the more restrictive this is, the better. That's the power of the theorem. Yeah, the fact that you get these good maps to Z is the power of the theorem. Okay, makes sense. Okay, so in fact, if you are happy to work in low dimensions, you can get slightly more sharp theorems. So in dimension 3, there's a very sharp theorem, but it's not new. But let me show you a dimension 4 result. Before you protest, hyperbolic manifolds in dimension 4 have non-zero Euler characteristics, so they will not fit into this. But there are other manifolds than hyperbolic manifolds. Okay, so if you take a reverse Poincaré duality group of dimension 4, then the following are equivalent. There is again a virtual epimorphism onto Z whose kernel is a Poincaré duality group of dimension 3. This is all over Z. This is the best Poincaré duality. There are no fields. Okay? This is over Z. If and only if the first and second L2 Betty numbers vanish. Okay? So you check two global invariants for the fundamental group of your 4 manifold, and you can show that it virtually fibers in this algebraic way. Okay? So if your game is finding exotic Poincaré duality groups of dimension 3, then maybe this is promising. I mean, if you can find interesting reverse 4 manifolds, then it might be a good game to play. Okay, but I don't think much is known about which 4 manifold groups are reverse beyond kind of easy examples, which immediately fall into this anyways. Okay, so the theorem can become a bit more powerful if you pass to low dimensions. Okay, I also want to go back for a second. So actually, we also have a version of this. This is coming back to your question. We also, if you assume that the Poincaré duality group is over Z, so you replace this with Z, then we can get the same statement for every field here, provided that we have this vanishing for every field.
So it's the same homomorphism to
It's the
Z
same.
that's working
Yes, it's the same finite index subgroup and the same up to Z, which works simultaneously for all fields.
But the kernel group, though, still isn't an FP
No.
and minus 1C.
No, that we cannot show. I mean, I would hope it is, but I don't know how. Okay, so let me go back to the audacious conjecture, still have time. So finite volume hyperbolic manifolds of all dimensions should be virtually fibered. So you can have your own opinion about this conjecture. However, if we add this assumption that the fundamental group is Riefers, which is often true in this setting, then I really do believe in this conjecture. Okay, so I think
Then it's a theorem.
No, then it's a belief. Then he believes
I believe in this conjecture more than in that.
But he only believes it when he.
This conjecture, I believe, maybe.
No, but for co-compact, it's not.
If not for, I mean, the simplest type guys in all dimensions are Riefers.
He only has theorems about algebraic fiber. He doesn't have theorems about
They-
fibering.
I'm sorry.
Yeah, that makes sense.
I see.
Yeah, I don't know how to pass from Poincaré duality back to the topology. Yeah. Okay.
Say again, which are the groups to be
Of simplest type. That's an official definition.
for a quadratic form of cube? Lower to the
What did you say? What did you say about the simple type?
The odd dimensional simplest type examples are all Riefers.
What?
Riefers, they have this property.
They all and the non-simple, it's no.
It's not known. I don't think there's any example of non-Riefers hyperbolic manifold known. So potentially they all have. Okay, but that's a job for somebody else. Okay, I'm happy to assume Riefers and move on with that. Okay, everybody happy? This conjecture more believable? Okay, that was the point. Okay, why do I think it's believable? So first of all, there is a very nice theorem of Dawid, which tells you that if you take a closed hyperbolic manifold of odd dimensions, then all of its L2 Betty numbers are actually zero. That's a fact. Then you can actually get rid of the closed using, I think, the work of Gaboriau. So it's true for all finite volume hyperbolic manifolds of odd dimensions. This is only for L2 Betty numbers with coefficient Q, and we don't know what happens if you take different ground field. I would conjecture, and I do now, okay, this is an official conjecture now, that they also are zero. The reason why I don't know how to prove it is that Dawid's theorem is very non-algebraic. Okay, it's very hard to algebraize this theorem. Okay, but anyways, I think it's, so this is a fact. This is not a fact, but I think it should be true. And once you have both of these things, then you are in this situation. So imagine that this conjecture is true, okay? With the theorem I mentioned, we can pass the finite index subgroup, which I kind of did already, and we're going to show that this fundamental group of our hyperbolic manifold maps onto Z. The kernel is now Poincaré duality over all fields, and it's extremely hard to believe that it will be something else than a fundamental group of a fiber. What else? I mean, how else would this? I don't know if it's finitely presented. If I knew it's finitely presented, it would be almost game over. If I knew it's Poincaré duality over Z and finitely presented, it's game over because Farrell's work does the trick. So I don't know that. You're right. Still, hard to believe. I would say that there's such an object in there. Okay, but that's the missing thing. And now I have 10 more minutes, so I'm going to actually use the board if I can find the chalk. And I find the chalk
Over there.
Over there.
Ah, perfect. Thank you. And let me tell you a couple of words about how it all works. Okay. So how does it work? So okay, proof. So there's one object I have to introduce, and then I will tell you how it makes an appearance. So if you have a group and a map onto Z, then I'm going to pick an element T in here, and this element is going to be mapped to the generator 1. And what I'm going to do is I'm going to take the group ring of G and think about it. There's a kernel of this guy. The kernel is going to be called K, just to confuse everybody. Kernel of phi. So I can think of this group ring as the group ring of the kernel, okay? And I'm going to take Laurent polynomials in T. Okay? What's happening here? An element here looks like this. Okay? And now an element in here looks like like that. And what I'm doing is I'm taking a G here and I'm rewriting this G in this form. That's all that happens. Okay? Every group element can be written as something in the kernel times T to some power. The power is exactly the image of G undefined. Yeah. So if I do that, I get this equality between the group ring and this polynomial ring with a slight issue, namely this T is not central in this ring. When I conjugate by T, I don't end up getting the same thing. So this is a twisted group ring. Okay? So you have to be careful when you push the T through. Okay, but it's very easy to understand what's going on. When you push T through, you just conjugate your elements. This T has an action on this coming from the conjugation action. Okay. But that's a little algebraic trick. And now once you know this, you can define the Novikov ring. The Novikov ring is just, this is the field, this is the kernel, and I'm going to take the Laurent power series, which I will denote like this. Okay, so this is Laurent power series. I'm allowing not just finite sums like this, but I'm allowing this I to start at minus something and go up to infinity. Yeah, I just make my object a little bigger. That means this is what people do in algebra, right? To pass from polynomials to power series. Yeah. Okay, so that's kind of a key player. And let me tell you why. So this took us a number of years to understand why this is really so important. And the important fact is the following. So here is my kg, and I'm going to think about it as kk polynomials. I'm going to embed it into this Novikov. Let me introduce. I didn't introduce notation for it. So the notation for this guy is going to be kg hat phi. Phi allows me to pick this element t, and it's exactly these t's that I allow to go to infinity. So this essentially tells me this is like the grouping of G, except I'm allowing things with infinite supports, provided that the support goes to infinity with phi. That's what happens. Okay, so I can take the group ring, I can embed it. Let me stay there. And I can embed it into the Novikov ring. And I can embed it into the Novikov ring of the other map to Z, namely minus phi. And now these guys, I can map the big product of k, e to the I, by I to Z. Okay, let me explain. So here we have sums of elements, finite sums of group elements with coefficients. Here we are allowing infinite sums. However, in this bit, the infinite sums can be infinite in the direction of phi, and here they can be infinite in the direction of minus phi. Whereas here in this big product, I'm allowing infinite sums which go to infinity both ways. Okay? In every slice, for every particular I see only finitely many, but it goes to infinity both ways. Yeah? So this certainly embeds into here, this embeds into here. The difference of the embeddings is exactly the stuff that is finitely supported. So this is an exact sequence. Okay? Everybody believes me? Think about the picture. This is...
How the left embedding? How it is embedded?
You can take this to be both identity, and this is embedding, not identity here and minus identity here. Yeah, does that make sense? I'm sorry, maybe I should. So if there's an element here, you can map it to x minus x. And if you have an element here, it just goes to... Does that make sense? So these guys are finitely supported. These guys are like supported infinitely in this way and in this way. And here you have things which are infinitely supported in both ways. Okay. 1 minute. So now, why do I care about this? Because if I have a short exact sequence of coefficients, I can get a long exact sequence of cohomology. So if I do that, I'm going to have this. What is this? This is the cohomology at infinity, or compactly supported cohomology of the classifying space at infinity. And this actually detects exactly whether you are Poincaré duality group or not. Okay? So I didn't show it, But a group is Poincaré duality if and only if this guy is 0 in all dimensions except the dimension of your Poincaré duality, and that dimension is just a single copy of the field. So if you can compute that for all i's, you will know if your group is Poincaré duality or not. Here, I'm going to have guys called Novikov homologies. Okay, and here I will have the cohomology of G with coefficients in this funny product. Okay, now, and then this goes on, right? I mean, this is part of a long exact sequence. This guy, by Shapiro's lemma, is the, should I use dimension? Correct? This guy, by Shapiro's lemma, is actually the cohomology of the kernel with coefficients in its own group ring. Okay? So the point is, and I need a color, the reason why I introduced this Novikov guy is that imagine what happens if it's 0. If we know that this homology is 0, then it tells me that this is the same as the previous guy. The previous guy is hi minus 1 k with coefficients in its own group ring. So if I can show vanishing of this Novikov homology, I get equality between cohomology at infinity of the group G and the kernel. And that's all I need to know to be able to say whether something is Poincaré duality or not. Okay, so this part of the picture allows me to push Poincaré duality down, provided that I have this vanishing. But this vanishing is exactly what you get for reverse groups if you know that you have vanishing of L2 homology. Okay, I will not explain this, but there's a trick which allows you to pass from L2 homology to this Novikov homology for reverse groups. That's how you get it. Okay, and I think that's it. Thank you.
Thank you very much for the very interesting talk. Are there any more questions? More questions?
So the condition RFR,
Reverse.
whatever, and it's really the major obstruction to classes.
You're being very negative, like you think of it as an obstruction. It's not an obstruction, it allows you to do anything. I mean, it would be crazy to expect that any of this is true in full generality, right? Am I answering your question? Sorry, I should shoot you down.
No.
So I don't know if it's an abstraction. I mean, it's all compact special groups have it.
All what?
All compact special groups have this property. So we know more and more groups which have it.
Any further questions? Not, then let's thank Dawid again.